Today, we're going to look at gases, chapter 13 in your textbook. There we go. All right. We have several topics to cover. Let's get started by asking the question, why do we study gases? Well, there are at least two answers to that question. One is historical. When modern chemistry was starting to emerge from the Middle Ages out of alchemy, the chemists of those days, which is actually it's a misapplication of the name. They weren't known as chemists in those days. They were known as natural philosophers, and their interests, those people who were studying the sciences, especially the physical sciences, were broad and largely encompassing everything that was known in the day. So there's a historical sense in which gases came first. They were reasonably well known from the Middle Ages, and instrumentation was available to quantify gases relatively easily and accurately. So we started with gases mainly for that reason. The other reason is that well, gases tended to behave similarly in a physical sense, regardless of what gas you were studying. And in those days, differentiation of gases was limited, but as long as we had these four factors quantified: pressure, volume, temperature, and later came moles, the number of particles in a gas. That came a little bit later, but as long as you had values for each one of those, you could completely describe a gas, and you could completely describe a gas in physical terms. And it didn't matter what kind of gas you had. Those terms would describe the physical behavior of any gas under what we consider normal conditions, 1 atmosphere pressure and room temperature. And they could readily be used to develop first laws and then theories about the way the real world worked. So the first breakthroughs in understanding in modern science and modern chemistry came from gases. And we're not just talking about physical characteristics of gases now. We're talking about the chemistry of gases. How do gases interact when they produce a chemical reaction, right? We need to know these factors, of course, but gases gave us huge amounts of information before we had a handle on solids and liquids. So what characterizes a gas? We go back to the beginning of this course, and we know that gases will expand to fill the container. So if you want to constrain a gas so that you know that you have that gas and nothing else, then the container must be sealed and can only be accessed through special ports. It also has, that means it has an indefinite volume and indefinite shape. It acquires the shape of the vessel and the volume of the vessel. Another characteristic of gases is that gases always form homogeneous mixtures. Right? That equals a solution. Two or more gases will mix perfectly with each other. Doesn't matter what the conditions are, as long as they're gases, they will mix in a homogeneous manner. And that just makes sense because the particles in gas we know now are very far apart in relation to their size. So there's lots of distance between the gases. There's plenty of room for everybody. Gases also exert pressure on their surroundings, right? So why is that? We want to know. We want to know why gases exert pressure, right? You stick a tire gauge on the valve and the tire holding your car up, and you get a measurement. Why is that? The reason is that the gas is pushing on the inside of that tire everywhere. And it just so happens that you access that pressure through a valve, then that push is delivered to the measuring device. Okay, so if we're going to take off from that last statement, gases exert pressure on their surroundings. We want to define what a pressure is. So we're going to take this first term and define it quantitatively. Okay, pressure is a force per unit area. Okay, that's the simplest definition. And as a consequence, it doesn't matter how much gas you have. If you measure a certain pressure, then it's going to be a force per area. And it may be a large area, a small area. If it's a large area, then the force will be large. If it's a small area, the force will be small. The ratio then gives you that pressure value, and it's independent of the amount. So that makes it an intensity factor or an intensive property. Now, if we're in SI units, right, the force must be in newtons. Newtons, which is abbreviated N. And the area has to be in square meters. Right? Newtons per square meter. And that's given a special derived unit of measure called the Pascal. Okay. So the square meter, of course, is a derived unit because the unit of length is the meter. But the Newton is also a derived unit. So we've got a derived unit from two derived units. Well, suppose you want to enter this pressure into a calculation that has other units of measure. Well, you can't cancel them, right? Combining them may be useful, but maybe you want to be able to cancel units so you come out with something that's more consistent with the measuring system. So we want to know, what is a Newton? Well, we go back to one of Newton's laws. Newton's second law of motion says this. Newton says that for a mass that's being influenced by a force will accelerate at a certain rate. And acceleration is velocity increasing or decreasing per unit time, right? So if this force is a Newton, which would be the same here, and the mass is in kilograms, right? What are the units for acceleration? Well, velocity is meters per second. Acceleration would be a change in meters per second. So that means acceleration would be meters per second squared, right? So a Newton is a kilogram meter per second squared. Okay. So if we put these values up here in this formula, then kilogram meters per second squared divided by meters squared. Okay. This is in the denominator. That's in the numerator. This is in the denominator. So this one cancels and leaves us with only one there. So now we have kilogram per meter second squared. So that would be equal to 1 Pascal. So the only reason I'm going through all of this units measure is so that you understand that these derived units are useful in and of themselves. But when you start putting them into calculations, you need to know what they're equal to, so that if your calculation has, say, kilograms in the denominator for another term, then those will cancel. Okay. So the SI unit is the Pascal. Pressure is one of those units of measure, one of those factors that has several possible units of measure. The Pascal is the standard. It's the SI unit. But other units may be more useful, and we're going to look at those right now. All right. So we've got units of measure here. We've got the Pascal. Then we have atmospheres. All right. 1 atmosphere is the pressure of the atmosphere on average at sea level. All right. And we can interconvert these, right? 1 atmosphere. Let's see, let's move this out here. 1 atmosphere equals 101,325 pascals. Okay. So now we have an equivalence. That means if we have measured pressure in pascals, we can convert it to atmospheres, or vice versa. All we need is that equivalence. All right. Another unit of measure based upon the invention of the barometer. We're going to talk about that in just a minute. This is also equal to 760 millimeters of mercury in our barometer. And that'll make more sense in a minute. That's also equal to 760 torr. That unit of measure is in honor of Evangelista Torricelli, who invented the barometer. And the Pascal is named after Blaise Pascal, who was a French mathematician, physicist. He was a polymath. Right? He dabbled in everything, which a lot of those 17th and 18th century scientists that we would call them now dabbled in lots of different things. Okay, this is Torricelli's invention, the barometer. So what was needed was, well, let me back up. Gases could easily be measured by volume, right? If volume was a well-established unit of measure, it may not have been a liter for all of the Middle Ages, of course, but eventually we settled on the liter. But we didn't have an easy way to measure pressure. So Torricelli came up with this device, which was actually a container of mercury and a long tube. That was open at one end, and that one end was submerged in the mercury. Now, before he put that tube in the mercury, he filled it up. Filled up the tube, turn it up, fill it up with mercury, put his thumb or his hand over the end of it, submerge it in the mercury, and then turn it loose and see what happened. Well, what happened is the mercury level dropped to somewhere in here, and at sea level, that distance between the top of this meniscus and the surface here is 760 millimeters. Okay, that's 1 atmosphere. Now, Torricelli reasoned that what he had up here first was a vacuum. Right? A vacuum, by definition, is a space that at one time had matter in it. It could have anything. In this case, it had mercury in it. Now it has nothing. Right? By definition, that's a vacuum. But what's holding up that column? There's nothing up here to apply suction. So there must be a force being applied here by the atmosphere. And that force is distributed through this liquid and is pushing up that column and holding the column up. So there must be a certain mass of atmosphere above this to apply the force that's required to hold that mass of mercury. In these days, glass blowers were very good at producing tubes of uniform diameter. So all Torricelli had to do was acquire some of these and fire, cut a length and fire the end of one end of it, and there he had his tube. But he had a choice of liquids. He needed a liquid because a solid wouldn't work because a solid won't flow. And a gas would kind of defeat the purpose because if you had a gas here, it would mix with the atmosphere and you wouldn't have a device. So it had to be a liquid. Okay, you had choices. Pure water was readily available. They understood distillation. Okay. So pure water could have been used. Problem with pure water is, if he even tried it, I don't know if he tried it or not, but if he tried it, the length of that tube would have to be about 33 feet. That would make a very good barometer. So he needed something that was denser than water, and he found it in mercury. Mercury was well understood how to handle mercury, except they didn't know about the toxicity thing. So this 33 feet in length now could be reduced to 760 millimeters, much shorter, made it more useful. Okay, that was the invention of the barometer. And since pressure is an intensive property, this vat could be any size at all. It didn't matter. And this tube could be any size at all. It doesn't matter. It doesn't matter how much. Pressure is an intensive property. So whatever is pushing down on this mercury will push up here in such a way as to produce a column that's about 760 millimeters high. Okay, I just explained that last one. Now, one thing that was done, once Torricelli publicized his invention, he and other scientists were using the barometer for other types of measurement. They would measure the air pressure, just set that barometer on your desk and watch it. And they eventually correlated the movement of the mercury column with the weather and found that for good weather, when good weather was coming, the column would rise. And when bad weather was going to come, it would drop. So we still associate good weather with high pressure and bad weather with low pressure. You could also take this barometer and throw it in the back of your ox cart and go up a mountain. And when you get to the top of the mountain, you'll notice that the level has dropped. So that confirms that as you go higher, there's less atmosphere above the barometer to push down on it. So it won't support the full column. It has to drop, a shorter column. Or you could go down to sea level or below sea level and watch the column rise. Okay. For a more practical use was to develop this into what's called a manometer. And a manometer uses a barometer to measure the pressure of an entrained gas, a gas in a vessel. Right? Let's see if I got a picture. Okay, that works. So we've got this gas trapped in a vessel, and it's pushing on this column of mercury. Now, what's the difference in the two heights of mercury? Right? You've got for the figure on the left, you've got a gas pressure inside this vessel that's less than atmospheric. So the atmospheric pressure is pushing so hard here, it actually supports this column of mercury. But that column of mercury is not at 1 atmosphere, right? Because there's gas in this vessel pushing back, right? So the total pressure inside that vessel is you have to subtract the atmospheric pressure from the height of that column. And that gives you what the difference is, the pressure pushing back on that column. So to put it mathematically, you would say the total pressure, right, is, let's see. Yeah, total pressure is the pressure of the gas plus pressure of the atmosphere. Okay. So we got a pressure inside. No, sorry. Atmospheric pressure is equal to the gas pressure plus the mercury pressure. So we got the pressure of the mercury column and the pressure of the gas is being supported against the pressure of the atmosphere. So if the pressure in the vessel is less than atmosphere, you're going to get a column of mercury on the vessel side. And if the pressure in the vessel is greater than atmosphere, you're going to get a column on the atmosphere side. That allows us to measure the pressure of a gas trapped in a vessel. Okay. Now, how do we know that there's pressure pushing down? Well, the barometer tells us that there is, but one dramatic way to demonstrate gas pressure, atmospheric pressure, is, and I've seen this done. My father used to do this as a teacher for his class every year. You take this empty paint can or turpentine can, and you put a little bit of water in the bottom of it. Doesn't take much. And then you leave the cap off of it and you heat it. You boil all the water until there's nothing but water vapor left inside, right? There's no air, just water vapor. Then you cap it and turn the burner off and let the can cool. And as it cools, the water condenses into a smaller volume. What's left behind? What's left behind is a vacuum. Because there was water vapor in it, now there's nothing. And the difference in pressure, since there's no pressure on the inside, you've got an atmosphere of pressure pushing on the outside, and it collapses the can. So here's an example of how we convert one pressure into another. It's simply an application of what we learned earlier, dimensional analysis. In this case, the pressure of the gas is measured at 2.5 atmospheres using that manometer. So we know that the pressure of the gas is equal to 2.5 atmospheres. Okay. What's the pressure in torr and pascals? Well, we have atmospheres here. We can convert to torr, right? We just need a unit, a conversion factor that puts atmospheres on the bottom and torr on the top, right? Then atmospheres cancel, leaves us with torr. And that first measurement, that first unit change, will be 1.9 times 10 to the third torr. Okay. What if we want to convert atmospheres to pascals? Well, we need another conversion factor. 1 atmosphere equals 101,325 pascals. So we multiply that times 2.5 atmospheres. And we get 2.5 times 10 to the 5th Pascal. Okay. Now, the advantage to using atmospheres or torr is that it's more convenient in many cases. But the advantage to using pascals is it's a derived unit of known factors. Right? We just gave you those kilograms and meters and seconds. So that means it's interconvertible with other SI units. Okay, so let's see what this one has to say. The vapor pressure over a beaker of hot water is measured as 656 torr. What is this pressure in atmospheres? All right, are we going to show? Oh, don't show it. Oh, yeah, we do. 56 torr We need a conversion factor for atmospheres. 1 atmosphere equals 760 torr. And that's 0.863 atmospheres. Now ask yourself, is that reasonable? Is that answer reasonable? 760 torr is 1 atmosphere. We know that. 656 torr is less than 760. So we should have less than 1 atmosphere. That seems reasonable. Okay. Now we're going to look at gas laws. Remember what a law is. A law simply says under certain conditions, quantitative or non-quantitative, under certain conditions, the outcome will be this. We don't try to say why. We don't make any, we cannot draw any conclusions about if we change something relative to the law. The only thing that can change are the factors that are given in the law. So we're going to look at the first one is gas law is Robert Boyle. Boyle's law. And we're going to take these in chronological order. Remember these 4 factors. Okay? In order to compare any 2 of these factors, the other 2 must be constant. So with Robert Boyle, we're going to compare, well, here's his experiment. But what we're comparing here is pressure versus volume of a gas. What happens to the volume when we change the pressure? So what does that mean in terms of, say, graphing the results? Well, if pressure is controlled and changed by the researcher, this is x-axis. That and the response, the dependent variable, is the y-axis. Okay. So what Robert Boyle did was he took one of these tubes that were very readily made, and he bent it into a J tube. That end is open. Okay, so it's filled with air. He started adding mercury to it. And it would pool up in the bottom and then pool more. And then when it touched that inner curve right there, that amount of gas, which we designate as N, moles, the amount of gas now is fixed. It will not change. So he kept adding mercury, and he noticed that this side was not as high as that side. Or he'd add some more, and it'd only come up here. So what he concluded was that this trapped gas was pushing back against the mercury. And the difference between the 2 levels here, that distance, height, was a measure of the pressure inside that container. And he also measured the length here. Since these tubes are uniform diameter, then the length was a representation of the volume. Right? Because we know for a cylinder, right? Cylinder volume is height times area. So if the area is constant, then the height will change directly proportional to the volume. Okay. Okay, what about the pressure though? what kind of pressure is being exerted on that gas? Well, two factors. This height here was the, say the tube pressure, but we were also getting atmospheric pressure. So the total pressure on that gas was atmospheric plus the tube pressure. So that tells me that Boyle also had a barometer sitting over there in his workshop, and he took that value against this value, plus that value. Right? And that gave him a set of data. And we now would represent that data as pressure versus volume, right? And we get a value here, a value here. And since this is X and this is Y, we can plot those on a graph, right? X is pressure, volume, and volume is going to be whatever we want it to be, right? You would put units here, you would put units there for pressure. Okay, this is a modern representation of Boyle's experiment. Okay. So we get a pressure of 29.1 inches of mercury, right? Oh, inches, wait a minute. I erased them all. Okay, let's say 1 atmosphere equals 101,000, let's see, 325 pascals. It's also equal to 760 millimeters of mercury, or 760 torr. And it's also equal to 29.92 inches of mercury. Okay, so there we have another conversion factor. The way the experiment is presented here, pressure is in inches of mercury and the volume is in cubic inches. Well, what Boyle discovered was if he takes any value of pressure and multiplies it times the volume, he gets a constant value. That constant value requires, this is fixed, or fixed. And this is fixed. Both temperature and moles must be constant. Or I should say constant. That would be a better term. Constant and constant. That will allow pressure and volume to vary, and we can compare them. What he found was that pressure times volume is always a constant within experimental error. And when you see some of that error there in that chart, right? Multiply the pressure in inches of mercury times the volume in cubic inches, and we get values close to 1,400. Okay. So what does that mean? That means if this product is equal to a constant, then pressure and volume are inversely proportional. If pressure goes up, volume must go down in order to retain that constant. Okay? What would it look like if you plotted it on that graph, though? You get something like this. You get a curve. Only this is a special kind of curve that you may have encountered in math class. It's called a hyperbola. Now, if we were in math class and we had all 4 quadrants represented here, this hyperbola would have a partner over there on that side. All right, remember that? But in the physical world, we've got positive pressures and positive volumes, and we don't need this part of the graph. Okay? All right. You will notice that mathematically speaking, anytime you have two variables in a product relationship times each other equal to a constant, they're always inversely proportional. Now the line is sloping from upper left to lower right, which means at any point on that curve, the slope could be calculated, say here, slope would be calculated there if it was here, slope would be calculated there, if it's here, slope would be calculated there. Notice that the slope is changing. It's always negative, right? Lower left, upper left to lower right, that's always a negative slope. But it's not constant. It's not a constant slope as presented. Hold on a second. Let me see. I don't want to steal my own thunder. Okay. I hope I've said it before. Scientists don't like curves if we can get away from them. If we can't, then we deal with them. But in this case, we can make a straight line out of that data. And here's how we do it. If we've got pressure times volume equals a constant, then let's do something mathematical that's permitted. Divide the whole equation through by volume. Right? Volume, volume. That's permitted. If we do the same thing to both sides, then we haven't changed the equivalence. That means that this volume cancels, leaves us with pressure equals K over V. All right, this is a constant. So let's factor out the volume. There we go. What does that look like? Y equals mx plus b. That is a straight line. So, and notice that b is 0. That's the y-intercept, right? The y-intercept is 0. So that means if we plot this on a graph, and this is 1 over v, then we'll pass through the origin and produce a straight line with a positive slope. So all you have to do to get a straight line out of x times y equals a constant is, or p times v equals a constant, just take the inverse of your volume measurements and plot each one of those against the pressure that's associated with it. That will give you a straight line. And a straight line is much, much easier to deal with than a hyperbola. Okay. Now there's another practical way to deal with Boyle's law. Okay. So if pressure times volume equals a constant, and we got this gas confined at a constant temperature and number of moles, then if we change the pressure and get a different volume, say this is the first situation, and then we change it to get a different set of numbers, we saw from the table that those values are equal to K. Right? So this K1 and K2 are equal to each other. Okay. So what's that mathematical law? If A equals B and B equals C, then A equals C. In that case, if we've got that same gas trapped and we change its pressure, then the volume will change. And this is what I call before and after. If we know the before conditions and we know one of the after conditions, we can solve for the other variable. Okay? Anytime you have an equation with only one unknown, you can solve for it. Okay. So how do we change, how do we apply more pressure and then let the volume change? Well, it's more convenient now rather than using one of those J tubes in mercury, which is slightly hazardous. We just use a cylinder with a movable piston, and we apply more pressure to the piston, and that can be measured as a volume change. Right? So how do we deal with this in practical terms? If you're given a problem, and in this case, a sample of helium gas, which initially occupies 12.4 liters at 23 degrees and 0.956 atmospheres, what volume will it occupy at 1.2 atmospheres, assuming that the temperature is constant? Well, the best way to deal with this is to first identify what type of problem is it. Is it a before and after? Well, if you have if you have one pressure and a second pressure and only one volume, then you've got a before and after situation. So we have to identify what are the initial conditions and what are the final conditions. So I put those up here. And extract the information from the problem. The reason I do that is because if you put the numbers in the wrong place of that formula, you'll get the wrong answer. So the initial conditions are 12.4 liters at a pressure of 0.956 atmospheres. And then we're changing the pressure to 1.20. And there's your unknown. So now you can plug those values into this formula. And solve for the unknown. All right. And I think that's where the animation is going here. There you go. As long as you get your numbers in the right place, that's the thinking part, then crunching the numbers is going to give you the right answer. 9.88 liters. Now, does that make sense? If we go from 0.95, less than 1 atmosphere, to greater than 1 atmosphere, the volume should decrease, and it does. Okay, that was the first law, Boyle's law. Now, why does Boyle's law come first, chronologically? Boyle's law comes first because volume was an inherited term from the Middle Ages. And pressure now can be quantified by using the mercury barometer or Boyle's modification of that barometer in his J tubes. That's why it came first. Now, if you were interested in what change what change can you expect in volume if you change the temperature? Well, the pressure has to be maintained constant, and the number of moles has to be constant. And if you do that, and you plot the data for Charles' law, let's try that again. Charles' law. Charles was interested in the relationship of volume and temperature of a gas. What was required was an accurate measure of temperature. Right? In Boyle's day, there were no accurate thermometers, right? It hadn't been invented yet. And what Charles discovered was that the relationship of volume and temperature equals a constant is a direct relationship. So we get a line with a positive slope, as demonstrated in that graph. If the temperature is measured in degrees Celsius and the volume in liters, you get a different graph for each different gas. But they're all directly proportional. Notice in that graph that if you that the solid lines are supposed to be measurements, and the dashed lines are extrapolations. All right. So notice that if we extrapolate the temperature, okay, we don't need this graph anymore. If we extrapolate, and this temperature is in degrees Celsius, and this volume can be in anything, we're going to say it's in liters. Then you take any one of those gases, and you have measurements that bring you, say, to here, and then you extrapolate. Supposing you decrease the temperature, at what point would its volume go to 0? At minus 273 degrees C, you could extrapolate to 0 volume. Now that's theoretical, because we know that gases are made of molecules, atoms and molecules, and they have volume. So it's never going to go down to 0. This is what we call an ideal gas. It stays a gas all the way down to absolute 0. Now, I don't know who else speculated, but I do know that Lord Kelvin did speculate, and he created a different measuring scale for the temperature called the Kelvin. And we put it on a different scale like this, right? So this is 0 K. And if we get to 0 degrees C, then that would be 273 K. All right. Now, what's the advantage of this? Well, this side is positive for Celsius and negative for Celsius. What would happen if we had this relationship here, and all of a sudden we flipped from positive to negative? What's that going to do to your constant? It's going to change the sign of your constant. Not constant anymore. So in order to maintain a positive value for that constant, we need a unit of measure for temperature that has no negative values in it, and that's Kelvin. So whenever you do a calculation for gases in this chapter, you have to convert to Kelvin. You cannot use Celsius. Now, Celsius is more convenient for measuring purposes, but for calculations, you have to have Kelvin. All right. Line is always positive slope. Right there, absolute zero for the temperature. Now, there are different slopes for different gases. And actually, we call it Charles' law, but Charles did not publish his work. He did experiments at the end of the 18th century, and a countryman of his who came along a little bit later used Charles' law relationships that he had learned probably through written correspondence. He learned of Charles' laws, the relationship, and this Frenchman gave credit in his publications, gave credit to Charles for this relationship. That's why we assign the name Charles' law to it. All right. Now you could 273.15 is 5 significant figures. 3 significant figures will work for our purposes, will work just as well. So if we find any discrepancies in our calculations, if they're very minor differences in our results and some published results, it's probably due to that factor. And we use the same reasoning here to give us our before and after relationship. Right. I think we talked about temperature and thermometers earlier in the semester. Right. Celsius developed his with a scale 0 to 100 degrees, and Fahrenheit developed his on a different scale. So we don't use Fahrenheit for most applications except for weather. But we do use Celsius. And the size unit of the degree in Celsius is the same size unit as Kelvin. So all we have to do is correct for the 0 point. The 0 point moves. Okay. So for this problem, we have a balloon containing, if it's going to be this relationship, we should set up V1, T1, V2, T2, and put our values in there. Suppose a balloon is 1.3 liters at 24.7 Celsius. 1.3 liters at 24.7 Celsius. And we submerge it in liquid nitrogen, which is at minus 195. We want to know what's at new volume. And the pressure didn't change. Only the temperature changed and the volume. And the number of moles didn't change because the balloon still has the same number of moles in it. Okay, so we would have to add 273 to this one and 273 to this one, and then plug our values in here, and this would be our unknown. Okay, so there's how we would set it up. and solve for our unknown, 0.341 liters. So it's about a third of a liter. It shrunk from 1.3 liters down to a third of a liter with that change of temperature. All right. Got another law coming up. Okay. Avogadro. Avogadro was an Italian, and his interest was, now that we could associate moles with these other factors, Avogadro wanted to know the relationship between volume and moles. So temperature must be constant and pressure must be constant. And in this case, say we have atmospheric pressure on the outside, but the piston is free to move. So how do we get more moles in there? Well, there has to be a valve, and we put a certain number of moles in there. If we double the number of moles, then we double the volume. If we triple the number of moles, we triple the volume. So we get a relationship for Avogadro of a direct relationship. As we increase the moles, we increase the volume. So let's see, V over N is a constant. And this was very shortly after Charles. Well, actually, it was about 30 years after Charles, but only about 10 years after Lussac. Volume and number of moles are directly related. Yeah, they're direct proportion. Okay. All right, that's a different way. If this is equal to the constant, right? If we flipped it, it would be the inverse of that constant. So we just change our constant. Let's be consistent with the slides. Number of moles, volume is constant. So if we use our relationship as before, we get a before and after relationship. It's a direct relationship between the two. Okay. So if we have 2.45, we want to solve this problem. We got to see, is this really a before and after? 2.45 moles occupies a volume of 89 liters. What volume will 2.10 moles of argon occupy? All right, so we have 2 moles and only 1 volume. So we're going to go N1, V1 into V2. So what are the initial conditions? 2.45 moles occupies a volume of 89 liters. And 2.10 mole occupies what volume? Well, what should we expect? We're decreasing the number of moles to here, so the volume should also decrease. And if we plug those into the formula and solve, we find that we do get a decrease in volume, 76.3 liters. All right. Before we leave Avogadro, I want to draw your attention to another way to express Avogadro's law. Avogadro said, if you have 2 gases doesn't matter what the gases are, just different gases, and they occupy one in this volume and one in this volume, and those volumes are equal. And they're maintained at the same temperature. And the pressure inside is exactly the same. It can be anything. As long as the pressures are equal, then it must be true. The number of particles of gas in this one are equal to the number of particles of gas in that one. We say moles now, but particles works also. All right. What's the significance of this relationship? Well, up until Avogadro's law, chemists, particularly in Europe, had no concept of how a chemical reaction was proceeding stoichiometrically. All they knew was mass. You put a mass of this together with a mass of that, and you get a product. And when their experiments or their manufacturing processes failed for some reason, they didn't know how to fix it because they didn't understand the stoichiometry of the reaction. So Avogadro's law says, here's your solution. If you've got a gas here and a gas here, and the masses of the gases are not equal, or we could say the mass of gas 2 is greater than the mass of gas 1. Why is that? The reason is, since you have the same number of particles, each particle of this gas must weigh more than each particle of that gas. Now we had a way to gather a relationship between mass and moles, and that eventually led to molar mass that we see on our periodic table now. And once chemists understood that relationship, now they were able to solve their problems with the help of Mendeleev, who created his periodic table using all the information he knew, plus this relationship. And this relationship wasn't published by Avogadro, it was published by his student, Cannizzaro. I think that's the way you spell it. It's either 2 Z's or 2 N's. Okay. So, before I introduce the ideal gas law, I want to talk about what is an ideal gas. Right? An ideal gas, first and foremost, is a gas under all conditions of pressure, temperature, pressure and temperature. The volume will change and the number of moles may change, but it's always a gas. That's an ideal gas. Now, when is a real gas? Approximately behaving like an ideal gas. Well, we haven't covered it yet, but under low pressure and high temperature. And as it turns out, low pressure and high temperature is room temperature and one atmosphere up to about I don't know, 20 or 30 atmospheres. So there's a lot of leeway in there. We can treat any gas as an ideal gas under these conditions. All right. So also one other thing before we go to the ideal gas law, I want to introduce you to the combined gas law. So we're going to start with, suppose you have a situation where all four of these values are variable. What are you going to do then? Well, let's start with this relationship. P1, V1 equals P2, V2. Right, we know that. Then introduce temperature. So V1 is related to temperature this way, and V2 temperature this way. Okay? And then moles and volume are related this way, right? This one and this one. There you have your combined gas law. P1 V1 over N1 T1 equals P2 V2 over N2 T2. If you have a before and after situation where you know, and you have to have all the measurements except for one. If only one unknown, then you can solve for it. That's the combined gas law. But what if you don't know where your gas came from? Under what conditions was the gas over here? Now it's over here, but you don't know that one. Now we need a gas law that will allow us to describe it in its current state. So before and after is one way, state function is another way. And that's where the ideal gas law comes in. All right, I'm going to show you where that came from. Right. If each one of these relationships is equal to a constant, then we can combine them all into a single constant. Well, these are both equal to the same constant, aren't they? Right. So we can leave that one out for now. All right. So if we rearrange this so that it's linear, then we have PV equals N K T. Only now we give K a special letter. We call it R. That's the ideal gas constant. Now here's the catch. With this equation, that constant has certain units of measure. The one we're going to be using is this one. It has measurement, it has values, units of measure, liter, atmospheres, per, mole, oops, not little, big K. There we go. Now, why is that important? Because if you use any other set of units, you get a different number. So if you use that one, then this temperature must be in Kelvin. This one has to be in moles. The volume must be in liters, and the pressure must be in atmospheres. So if you're going to use this state function, your units of measure are critical. The before and after situation, the only one you had to worry about was temperature. And the rest of them could be anything. But now we use one of these with those units of measure. You got to be sure that all of your units comply with those conditions. So now if we're faced with an automobile tire at 23 degrees with an internal volume of 25 liters, and you fill it with air to a total pressure of 3.18 atmospheres, number of moles of air in that tire. That's not a before and after situation because you don't have a before. You only have an after. You only have a present condition. So that means we have to use the ideal gas law. We're going to solve it for moles. Then we're going to change the temperature to Kelvin, like we did before. Be sure that the volume is in liters. Yes. Be sure that the pressure is in atmospheres. Yes. And there's our constant. And we can solve it, canceling units to be sure. And we get 3.27 moles of air in that tire. Remember, up to this point, we've only discussed gases in terms of laws. Okay, there's another exercise. This one is going to solve for pressure. And we know that we have to use the ideal gas equation because we only get one value for each of our factors. We can't use before and after. But notice that 5.67 kilograms of helium is not moles. We have to convert kilograms to moles. That's what this first term is, right? Moles. We're converting that first to grams and then using the molar mass to convert to moles. Then we can complete the calculation. Turns out we have 114 atmospheres in that tank, which is pretty high. There's probably some error introduced here because this is such a high pressure. Okay. At what temperature does 121 milliliters of CO2 at 27 degrees and 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.4 atmospheres? Notice that we have two volumes. We have one temperature, which is constant. And we want to find out the temperature when the pressure goes from 1.05 to 1.40. So this is a before and after situation. We're going to use the combined gas law. Only what this animation is doing is it's creating the combined gas law. The number of moles didn't change. So when you have the combined gas law, and the number of moles are constant, then that factor drops out. Now that's what you got left. And if we also hold the temperature constant, say theoretically, then you're back to Boyle's law. So if you know the combined gas law, you can recreate any one of the previous three laws. Now we're going to put the values in. And we find out that at temperature 969 K, we have these secondary conditions. Subtract 273, we have 696 degrees Celsius. That's pretty warm. Okay, another law. This was proposed by John Dalton, who gave us the atomic theory. So he wasn't just delving in that line of work. He was looking at a number of things. So what Dalton said was, law of partial pressures. He said that if you measure the pressure in a container, that pressure, and you have a mixture of gases in there, then that pressure is an arithmetic summation of the pressures that would be exerted by the individual gases if they were separated. Those are the partial pressures. So this gas has a pressure of its own. That gas has a pressure. This gas has a pressure. And the total pressure is simply the summation of those pressures. It's very simple. Okay. So if you have 1.75 moles of helium under these conditions, then it will exert a pressure of 8.4 atmospheres. But if you have a combination of hydrogen, helium, and neon in that central part of the picture, and you add all the moles up and you get the same total moles as you did with pure helium, you'll get the same pressure. So what this also says is that the number of moles, the 0.75 moles of hydrogen to 1.75, the 1.75 mole total is a value that will help us reason the total pressure. And this is, let's see, where's my calculator? .75 divided by 1.75 is 0.429. Okay, that fraction. If you do that for each one, say the helium would be the same thing. This is for hydrogen. Helium will be also. And then the last one, neon, is 0.25. 0.25 moles of neon over 1.75 moles total equals 0.143. Okay, if you add these up, .429 and 0.143, you get 1. Okay, what I've just described to you is called the mole fraction. That's equal to mole fraction of hydrogen, mole fraction of helium, and this one is mole fraction of neon. The mole fraction is in the same proportion as the moles of gas. And we can say all of this because the volume of the particles is negligible. These gases generally behave ideally. as if they have no volume. And the forces among the different gases are negligible also. They don't impact one another very frequently as compared to liquids and solids. All right. Let me see. All right. See if hoping I've got enough time here. So here's a practical experiment where we have potassium chlorate is being heated and it decomposes. Right? So potassium chlorate solid, if it's heated, will produce potassium chloride solid plus oxygen gas. Right? And that oxygen gas is being delivered by a tube into this container that was once filled with water. Now it's filled with oxygen gas plus water vapor. We're bubbling that oxygen through water, so it picks up water vapor. Now we have a combination. So the volume, or the pressure, actually, the pressure inside that container is equal to the pressure of water vapor plus the pressure of the oxygen. Right? We can measure the pressure, total pressure. What we need to know is what's the pressure of water vapor at that given temperature. And there are tables that tell you exactly that value. And since pressure is an intensive property, it doesn't matter how much you have. If you know the temperature, you can infer the pressure. There's the reaction. Oh, I didn't balance it yet. 2 and 3. There we go. Now it's balanced. Oops, not quite. There we go. That's right. So here's one of those charts that tells you, all right, what pressure inside that vessel is due to the water vapor. And we just need to know the temperature. Right? And the temperature, the pressure of oxygen will be the total pressure minus the pressure of water vapor. Okay. I don't have a problem for you to do there. There are problems like that in your review document. Okay. So let's use Dalton's law of partial pressures to solve this question. Say we have two vessels connected by a stopcock. Okay. This one has 9 liters at 2 atmospheres. And the smaller one is 3 atmospheres at 3 liters. Well, let's be consistent. Make that atmospheres and 3 liters. Okay. What will be the final pressure if we open that valve and let the gases mix? Okay. The temperature remains constant at 45 degrees. So we've got pressure and volume. what do you think the pressure is going to be, semi-quantitatively? If this one's at 2 atmospheres and that one's at 3 atmospheres, which way is the gas going to move? It's going to go that way until the pressures are equalized. And the total pressure is going to be between 2 and 3 atmospheres, right? It can't be greater and it won't be less. Okay, how do we approach this problem? Well, if we knew what the pressure would be with this gas expanding into that volume, say there's nothing there, if there's a vacuum there, what would the pressure be? Then we turn around and say, okay, let's make this a vacuum. And that one expand into this space. Then you get a pressure there. Well, the total pressure, according to Dalton, is going to be a summation of the two. Because when you open the valve, you get a mixing. And you get a pressure due to this one and a pressure due to that one. So the total pressure is going to be the pressure of the large one plus the pressure of the small one. Okay. So all we have to do is apply Boyle's law. Right? P1 V1 equals P2 V2. What's the beginning pressure? Beginning pressure is 2 atmospheres. Beginning volume is 9 liters. Final pressure, we don't know. What's the final volume? I'll move that one over here. The final volume is 9 plus 3 is 12 liters. Okay, so that gives us the pressure due to this side. So that's 18 divided by 12 is 1.5 atmospheres. And we do the same thing on this side. Only now it's 3 atmospheres times 3 liters divided by the same volume. So we get 9 divided by 12. We get 0.75 atmospheres. So the total pressure now is going to be 1.50 plus 0.75 or 2.25 atmospheres. Okay. So we calculated something between 2 and 3. Okay, here we go animated. Consider 2 separate calculations. For one side is a vacuum, and for the other side's a vacuum. There we go. Add them together according to Dalton's law of partial pressures. The final pressure will be 2.25 atmospheres, and you can measure it and test it. Should be just that. All right. Okay. 27.4 liter of oxygen gas at 25 degrees and 1.3 atmospheres. And 8.5 liter of helium gas at 25 degrees and 2 atmospheres were pumped into a tank with a volume of 5.81 liters at 25 degrees C. What's the question? What's the new partial pressure of oxygen? Well, we're starting off, this is a before and after for oxygen, right? The temperature doesn't change. 27.4 liters of oxygen gas and 1.3 liters at 1.3 liters are pumped into a container that now has a volume of 5.81 liters, we can calculate the partial pressure of oxygen. We can do the same thing for helium, and then we can calculate the total pressure of both gases. So this is oxygen, right? We use Boyle's law. We find that oxygen now has 6.13 atmospheres, right? It went in it went in at 1.3 atmospheres and 27.4 liters, but now we've compressed it into 5.81 liters, so the pressure goes up to 6.13. Do the same thing for helium, and its pressure went up a little bit, 8.5 liters down to 6.13. And then the total pressure is just going to be the summation. So we should measure a pressure in that vessel of 9.06 atmosphere. All right, this is just a reminder. A law is a generalization of observed behavior, has no intention of saying why. If we have similar systems, we can predict the outcome. But if we substantially change the system, then the law may not be valid anymore. If we have a theory, then we take the model that was being used for the law and we actually change the model. And now what we're going to talk about is a theory. This theory, the kinetic molecular theory of gases. Kinetic molecular theory of gases attempts to explain why gases behave the way they do. Why do they produce Boyle's law or Charles' law or Avogadro's law, or put them all together? Why do they describe the combined law? Or why can we use the ideal gas law? The kinetic molecular theory attempts to explain why those laws are valid. These are postulates. Postulate is a starting point. These are assumptions from which we move into the theory. Okay? Gases consist of tiny particles, atoms and molecules, very tiny particles. They're so small that the distance between them compared to their volume or their size is huge. In other words, the size of the gas particles doesn't matter. It's negligible. These particles are in constant motion. They collide with one another. They collide with the walls of the container. And when they do that, they produce a measurable pressure. Now, we assume these gases are ideal. In other words, in terms of the molecular theory, the kinetic molecular theory, these gases do not attract one another or repel one another. They just act like billiard balls. When they do impact one another, they just bounce off. There's no interaction at all. There's just a transfer of momentum. Now, since these particles do have mass, they do have volume, they do have mass, then each particle has kinetic energy, right? Kinetic energy for any object is equal to 1/2 its mass times its velocity squared. So any mass that's moving has kinetic energy. Well, the average kinetic energy of all these gas particles is proportional to the temperature. All right. So what does that mean? That means we increase the temperature, you increase the average kinetic energy of all the particles. Now, does that mean that every particle in that gas has the same kinetic energy? No, it's a distribution. We're talking statistics here. You get a distribution here of number of particles. Let's see, number of particles and temperature. So at low temperature, you have very few of them here. At the average temperature, you have most of them there. And then at higher temperatures, you're still going to get some, but most of them are right here. That's the average. The Kelvin temperature represents the average of kinetic energies. All right. So how do we explain the relationship between pressure and temperature? Gas pressure increases as temperature increases because the particles speed up. So if we were to look at this P1, T1, well, actually, let's use the ideal gas equation. PV equals nRT. So as temperature increases, pressure has to increase. All right. That's demonstrated with the law. Now, why is that? Well, as you increase the temperature, you increase the kinetic energy of all the particles. So when the particles strike the walls of the container and bounce off, they are pushing against the walls. That contributes to pressure. And if they got more kinetic energy, their mass didn't change, so their velocity must change. They strike the wall with more velocity, then you feel more force. And the average of all these billions of gas particles striking the walls can be measured as a pressure. How about volume and temperature? Well, if the pressure is constant, then if you get more strikes, right? Oh, volume and temperature. If you get the same number of strikes against this surface, but each one has more force because it's moving faster, then you get an increase in volume because the pressure is constant. So that piston has to move up. Okay. So we're holding two balloons. How are they related? One's got helium and one has hydrogen. Let's complete each of these statements saying different or the same. All right. Next slide. The pressure of the gas in the two balloons would be what? Well, they're under the same atmospheric conditions, so the pressure has to be equal, right? It has to be the same. They're in equilibrium with the atmospheric pressure and the force of stretching the balloons. Okay, next slide. This question, the temperature of the gas in the two balloons would be what? Be the same because they're in equilibrium with their environment. Okay. Number of moles of gas in the two balloons would be the same because of Avogadro's law. If the temperature is the same, the volume's the same, and we assume that, I think we were given that as an initial condition. Volume's the same, temperature's the same, pressure's the same, the number of moles must be the same. Okay? Here's the kicker. The densities of the gas in the two balloons are different. They have the same number of particles, but each particle has a different mass. Helium has a greater mass than two hydrogens. Right. Molar mass of hydrogen gas is going to be 2.02 grams per mole, whereas helium is going to be about 4 grams per mole. So helium particles are about twice as massive as hydrogen. That means if they're the same volume and density equals mass per unit volume, if the volume is the same, then the masses must be different. And the densities would also be different. All right. Sketch a graph of pressure versus volume at a constant temperature in moles. Right, there it is. That's your hyperbola. One, I didn't mention this as a reminder. What's characteristic of a hyperbola? Notice that the tails of that curve trail off. The tail heading toward the pressure side or the volume side will never touch the axis, ever, never, ever. Because look, if pressure times volume equals a constant, if the one heading toward the pressure ever touched the pressure, that means volume is 0. And then K goes to 0. It's not constant anymore, right? So those tails never touch the axis, no matter how far you take them. How about volume versus temperature? There you go. It's a straight line with a positive slope. Volume versus moles, straight line with a positive slope. Okay. Let's see, I think we got enough time to finish our discussion. Well, we're going to run over a little bit. So the volume of neon in its red balloon is twice the volume of the argon balloon. So V neon equals 2 V argon. Which of the following best represents the mass ratio of neon and argon? Well, if argon is half the volume, neon is twice the volume, that means you have twice as many moles. So the moles of neon equals twice as many moles as argon. This one is 20 grams per mole. And this was 40 grams per mole. All right. How many particles are in argon? The argon has half as many particles as the neon. Right? Has half as many particles. So that means it would have roughly 20 grams as compared to 20 grams of neon. So the ratio is 1 to 1. Mass ratio is 1 to 1. Okay, let's say we have nitrogen gas in a container fitted with a piston. It's under pressure of 6 atmospheres. The gas is at 45 degrees and a volume of 6 liters. You then cool the gas sample. All right. Which best contains the final result that occurs once the gas sample is cooled? Okay. What would happen if we cool that gas? Well, the pressure is going to be the same because it's an external pressure. Right? Pressure won't change. But if we cool it, the volume should decrease. The number of moles won't change either because there's no way to get moles in and out of there. So we're talking about a relationship of volume to temperature. And that's a direct proportion. Right? The volume of the gas decreases. So D is a good answer. The pressure of the gas doesn't change. So the only one that describes it accurately is D. The volume of the gas decreases. That was a qualitative expression. Now, how about a quantitative? The gas sample is then cooled to 15 degrees. So this is a new condition. We're saying that volume and temperature now are related. So we build our chart and we put in the values for V1, T1, V2, T2. Oh, V2 is unknown. So then we change the temperatures to Kelvin and we insert them in the correct position in our formula and find out the new volume is actually 5.43 liters. So what's the molar volume of an ideal gas? We can use the ideal gas equation to answer that question. Pressure, volume, and RT. We want to know the molar volume, the volume per mole. So we want to know this ratio. And we have RT over P. Right? So if we plug in R, 0.08206 liter atmosphere per mole K, right? And temperature. So what's the temperature? Well, at 0 degrees, that would be 273 plus 0 is 273. Right? And then what's the pressure? Pressure is in atmosphere. Standard pressure is 1 atmosphere. Okay? So if we solve that equation, let's see, 0.08206 times 273 divided by 1. That's equal to 22.4 liters per mole. Atmospheres cancel, Kelvin cancel, and we have units of liters per mole. 22.4 liter per mole is the molar mass of an ideal gas. So for gases, the standard temperature is 0 degrees Celsius or 273 K. And standard pressure is 1 atmosphere. All right, let's see. Is this the last slide? Close to it. Close to the last slide. Okay, a sample of oxygen gas has a volume of 2.5 liters. How many grams of oxygen are present? Dimensional analysis should get us the answer. 2.5 liters. If we know the molar mass, right, 22.4, we can calculate the number of moles and then use 32 grams of oxygen, right, 16 for each oxygen and 32 total, and convert moles to grams. Right, 3.57 grams of oxygen is 2.5 liters at standard temperature and pressure. Method 2 is use the ideal gas law. 1 atmosphere, right, times liters, and then there's the moles. And we solve that one, we should get the number of moles. There we go. Convert that, and we get the same mass. How about this equation, right? Where's the gas in this equation? It's hydrogen, hydrogen gas. So 15 grams of solid zinc react with 100 milliliters of 4 molar hydrochloric acid. What volume of hydrogen gas is produced at 25 degrees in 1 atmosphere? All right. So we have zinc. Oops. Not this one. Zinc plus hydrochloric acid yields, and let's see, 2, I think, right? Yep, 2. Aqueous plus hydrogen gas. I think that's balanced. 15 grams of solid zinc. 15 grams here. And hydrochloric acid is 100 mils of 4 molar. 100 milliliters of 4, oops, begin, molar. And we want to know volume. Okay. We can't get over there. And this is 25 degrees in 1 atmosphere. So temperature equals 25 degrees C, and pressure is 1 atmosphere. Okay, we got to use stoichiometry to get over here before we can use any gas laws. So what's the reaction here? Well, 100 milliliters is, 100 milliliters is how many moles? Well, this is 0.1000 liters, right? 1, 2, 3. So 0.1 times this is 0.400 moles of HCl. How many moles is that zinc? Well, we have to convert. 15 grams of zinc, molar mass of zinc is 6538. That's how many moles of zinc. Let's see. 15 divided by 65.38 is 0.2294 moles. Okay. Which one is limiting? Well, the ratio is 2 to 1. So 0.4 needs 0.2. Right? 0.2 moles of zinc required for 0.4 moles of HCl. So we're going to have 0.0294 moles left over. This is limiting. So we're going to use this number of moles to convert to hydrogen. HCl, H2, this is 1, this is 2. So half of that is 0.2 moles of hydrogen gas. Okay, now we have moles. We want to find out what the volume is. PV equals nRT. So volume equals nRT over P. Right, the number of moles is 0.2 moles. Gas constant. Liter atmospheres per mole. Okay. And temperature is 25 plus 273, right, which would be 298 K. So 298 K goes here, divided by 1 atmosphere. Okay, So now all we have to do is crunch some numbers. Let's see. Let me do that again, just to be sure. 826 and 298. I still don't trust myself. Let me do it again. I might have hit the wrong button. Yeah. So this is volume equals 4.89 liters. Here it is. Oh, I worked it out. There's our comparison to see which one is limiting. It turns out we only get 0.2 moles of hydrogen, not 0.2294. We get the least amount. There we go. Then there's the conversion to volume, 4.89 liter. Okay, I explained this earlier. Why is the plot of Boyle's law curved? And how do you get a straight line out of it? Right, I described that earlier. Just take the inverse of volume and plot pressure against volume, and you get a straight line. All right. That's it for chapter 13. And I will add, let's see, this is the third, a week from today. There will be no class. You will continue, of course. Most of you don't attend class anyway. So just continue with your homework and your preparations for exams. I will not be zoomed in on the 10th of April. I'll be out of town. So just continue with your work. And what we'll do is next Tuesday, we'll do a review on this chapter. Right. Next Tuesday would be the 8th, April 8th. We'll do a review. And then that following Thursday, I'll be out of town. Normally, I'd zoom in just for question and answers anyway, so you won't be missing much. But you can contact me on my cell phone if you need to. Text me or call. Text is probably better. All right, that's it for today, and we'll end the meeting.